Like many major scientific discoveries, radiation was found by accident. In 1896, French physicist Henri Becquerel was investigating phosphorescence, which occurs when light falls on a substance that then emits light of a different color. Becquerel wanted to know whether phosphorescent minerals also emitted X-rays, which had been discovered by Wilhelm Röntgen a year earlier. To find out, he placed one of these minerals on top of a photographic plate that was wrapped in thick black paper and exposed both to the sun. The experiment worked. The plate darkened. The mineral appeared to have emitted X-rays. Becquerel also showed that metals would block the rays that caused the plate to darken. The next day was cloudy, so he could not repeat the experiment. He left the mineral on a photographic plate in a drawer, but the plate still darkened, even without the sunshine. He realized that the mineral must have an internal source of energy, which turned out to be the result of the breakdown of atoms of uranium in the mineral he was using. He had detected radioactivity. Rays produced by atoms. Following Becquerel's discovery, his Polish doctoral student, Marie Curie, decided to investigate these new rays. Using an electrometer, a device for measuring electrical current, she found that air around a sample of a uranium-containing mineral was conducting electricity. The level of electrical activity depended only on the amount of uranium present, not on the total mass of the mineral, which included elements other than uranium. This led her to the belief that the radioactivity came from the uranium atoms themselves, and not from any reactions between uranium and other elements. Curie soon found that some minerals that contained uranium were more radioactive than uranium itself, and wondered whether these minerals contained another substance, one that was more active than uranium. By 1898, she had identified thorium as another radioactive element. She rushed to present her findings in a paper to the Académie des Sciences, but the discovery of thorium's radioactive properties had already been published. The scientist couple, Curie and her husband Pierre, worked together to discover the additional radioactive elements responsible for the high activity of the uranium-rich minerals pitchblende and chalcolite. By the end of 1898, they had announced the discovery of two new elements, which they called polonium, after her native country, Poland, and radium. They attempted to prove their discoveries by obtaining pure samples of the two elements, but it was not until 1902 that they obtained 0.003 ounces, 0.1 g of radium chloride from a metric ton of pitchblende. During this time, the Curies published dozens of scientific papers, including one outlining their discovery that radium could help to destroy tumors. They did not patent these discoveries, but in 1903, they were jointly awarded the Nobel Prize in Physics, along with Becquerel. Marie continued her scientific work after her husband's death in 1906 and succeeded in isolating a pure sample of radium in 1910. In 1911, she was awarded the Nobel Prize in Chemistry, becoming the first person to win or share in two prizes. Half-life. As a radioactive material decays, the atoms of the radioactive element change to other elements, and so the number of unstable atoms reduces with time. The fewer unstable atoms there are, the less radioactivity will be produced. The reduction in activity of a radioactive isotope is measured by its half-life. This is the time it takes for the activity to halve, which is the same as saying the time for the number of unstable atoms in a sample to halve. For example, the isotope technetium-99 meters is widely used in medicine and has a half-life of 6 hours. This means that 6 hours after a dose is injected into a patient, the activity will be half of its original level. 12 hours after injection, the activity will be 1/4 of the original level, and so on. By contrast, uranium-235 has a half-life of over 700 million years. Radioactive dating. This idea of half-life can be used to date minerals or other materials. Many different radioactive elements with known half-lives can be used to do this, but one of the best known is carbon. The most common isotope of carbon is carbon-12, with 6 protons and 6 neutrons in each atom. Carbon-12 makes up 99% of the carbon found on Earth and has a stable nucleus. A tiny proportion of the carbon is carbon-14, which has 2 extra neutrons. This unstable isotope has a half-life of 5,730 years. Carbon-14 is constantly being produced in the upper atmosphere as nitrogen atoms are bombarded with cosmic rays. This means there is a relatively constant ratio of carbon-12 to carbon-14 in the atmosphere. Since photosynthesizing plants take in carbon dioxide from the atmosphere, and our food consists of plants, or animals that have eaten plants, there is also a relatively constant proportion in plants and animals while they are alive, even though the carbon-14 is constantly decaying. When an organism dies, no more carbon-14 is taken into its body, while the carbon-14 already there continues to decay. By measuring the ratio of carbon-12 to carbon-14 in the body, scientists can figure out how long ago the organism died. This radiometric method is used to date wood, charcoal, bone, and shells. There are natural variations in the ratios of the carbon isotopes, but dates can be cross-checked with other dating methods such as tree rings, and the corrections applied to objects of similar age. A wonder treatment. Curie realized that radioactivity had medicinal uses. During World War I, she used the small amount of radium she had extracted to produce radon gas, a radioactive gas produced when radium decays. This was sealed into glass tubes and inserted into patients' bodies to kill diseased tissue. It was seen as a wonder cure and even marketed in beauty treatments to help firm up aging skin. It was only later that the importance of using materials with a short half-life was recognized. Radioactive isotopes are also widely used in medical imaging to diagnose disease and in treatment of cancer. Gamma rays are used to sterilize surgical instruments and even food to increase its shelf life. Gamma ray emitters can be used for the internal inspection of metal objects, to detect cracks, or to inspect the contents of cargo containers to identify contraband.